week is a seminar by Professor Mike Trott about geometric SMEFT, and yeah, please start. Yes.
Okay, thank you. And I wanted to thank the organizers for very kindly accommodating my suggestion of trying to have a culminating seminar after a bunch of lectures that were more introductory. And I hope it works out. And the idea is that in the last couple of sessions, a lot of things have been shown to you which are kind of bottom up and straightforward, which are also a bit historical in terms of how things have developed. But I tried to emphasize in a number of points how there's been problems, and then continuously the solutions of these problems have pushed us in the direction of thinking geometrically in terms of the standard model EFT in particular, but also more generally in terms of field theory. And I think at this point in time, it's becoming clear to a larger and larger number of people that something interesting is happening in terms of how our thinking about field theory is being changed, motivated in particular by these EFT results that you're going to see. So, and I think I just want to emphasize it's quite general, and I'll try and emphasize the generality of which this is a specific example of how thinking geometrically is kind of changing how we're doing things. So I wanted to also give credit to people that have been working on this who are junior. And the people that have been working on this that are junior that have gone through the Copenhagen group, which I run, are the people in black and white here. When you go through Copenhagen, you get a black and white photograph because they insist on doing an artistic photograph when you're in the group. I don't know why, but it's just a policy. This is Jim Talbert, and this is Tyler Corbett and Andreas Helset. And Tyler is now going to be going to Vienna in a month, and Andreas is a postdoc at Caltech working with Cliff Chung. And you can see that there's a spurt of papers here, which you've seen a bunch of these results over the last couple of days, but I'm going to try and put this in a more coherent picture now for you. And you can see how their names are color-coded and how they're appearing here, and also how other groups are now really taking off and doing this sort of thing, including Cliff, who you heard from earlier this week. So let me try and give you a little bit of a more coherent and constructed and a little bit of a higher level, perhaps, discussion on this geometric SMEFT and why it's actually working as well as it is. So one thing I emphasized and one thing that you saw was that there's a challenge even at dimension 6 in the SMEFT. And this is basically something that you can overcome by brute force, but this challenge gets worse as you go to higher operator mass dimension. That's one of the things the geometric approach comes in to clean up a lot, as you'll see. So what is the challenge? Well, the challenge is essentially, there's a lot of different aspects of it, but one thing that's a challenge is that there's a large number of parameters. And so you want to organize your thinking around this large number of parameters in some way that makes you be able to coherently calculate and make progress. The large number of parameters I emphasized are oriented and thought about in terms of symmetry, like whether you have 3 generations or 1 generation is a big difference in terms of number of parameters. CP violating or CP conserving effects are, of course, a way to distinguish the parameters. But that's just a lot of parameters in general. It's just a lot. Even though there are some symmetries around relating these parameters and how they appear in experimental results is generally a small subset of these, it's just a bit intimidating. So it's one of the reasons why I think it took a while for us to really push forward to dimension 8, and then by doing that push forward to dimension 8, we realized thinking geometrically makes it so much easier, not just at dimension 8, but also at dimension 6 in how we think about the field theory. So it's not just that there's a lot of parameters, it's that they do some weird things when you first see it. When you're doing an effective field theory, which has a spontaneously broken symmetry, or non-manifest symmetry more properly, and you have something like the Higgs field around, things like this happen at dimension 6, and when we first met this during the normalization efforts in 2013, I got to admit, it confused us for a little while. Like it threw us for about a week and a half or so. It was a bit confusing as to how to think about things. So what happens just at dimension 6 in terms of these parameters? At dimension 6 in terms of these parameters, when you want to go from the weak to the mass eigenstate basis, you modify the mixing angle, as you saw before, but you also have this explicit appearance of this Wilson coefficient times v squared over lambda squared. And that modifies how you're thinking of going from weak to mass eigenstates. So you can just figure this sort of thing out, and indeed this actually was first figured out in that paper I referred to when I was mentioning the W mass. The paper by Grinstein and Wise is when this was first written down, as far as I know. But it's a bit curious, and you might wonder and worry about how does this generalize to dimension 8 or dimension 10 or dimension 12? How complicated does this get, just on basic grounds? The Wilson coefficient CHWB, which is there, is also appearing in this redefinition. So there's this correlated thing happening in terms of the appearance of the Wilson coefficient, changing the meaning of the W, change the meaning of the Z and the photon. And it's just a bit interesting how that even happens at dimension 6. That same Wilson coefficient modifies the mass of the Z, and then combinations also come in to modify the mass of the Z, and one of these appears in the rho parameter. And it's kind of straightforward. At dimension 6, you can just brute force it. The covariant derivative can be worked out. You can work in canonically normalized coordinates field coordinates. And those are what the bars are really about in terms of the interpretation of things at dimension 6. We had to canonically normalize the theory, and we did so. And that's what these are canonically normalized gauge couplings. So you do a correlated transformation on the gauge coupling and on the fields themselves so that the cross terms, the linear terms, remain unchanged. But this you can just work out, and again, CHWB appears in here in these canonically normalized gauge couplings and mixing angles. So, you know, at the end of the day, you just brute force this thing, you just do it, and people did this and it got into codes, people are doing this with calculations at dimension 6, but you might worry how complicated is this at dimension 8 and dimension 10 and dimension 12? Can we even really do this sort of thing at higher mass dimension? So it's not just that there's a lot of parameters, it's not just that they're complicated, it's not also that, it's something else I emphasize too, is that you have to worry about how you numerically assign the value to Lagrangian parameters. Right? So that this dimension 6 operator, when you infer the VEV, has these corrections which we talked about a little bit in some of those other discussions. Right? And so you have to keep that at dimension 6, but you have to do this at dimension 8 and 10 and 12. So if we're going to really push from dimension 6 to dimension 8, dimension 10, dimension 12, worrying about higher order effects, in particular dimension 6 to dimension 8, we would have to redo all of this sort of thing and include all of these things which have to do with redefining the input parameters as well. And that might seem to be a very big task and a very big job, but it's actually a solved a situation in terms of closed form at this time using geometric approaches. So one thing to also emphasize on the way is that the dimension 6 stuff was brute force and the dimension stuff went in code. And what's in the code in SMEFT sim is actually consistent with all the geometric stuff I'm going to tell you about. Just FYI, if you use this code at dimension 6 and you just then add things at dimension 8 and loop corrections and that sort of thing, it's consistent, completely consistent, that code base. Because we basically just brute forced it and did it correctly bottom up, and then how we did it correctly bottom up basically grew into the geometric approach. Okay? So what people are doing now is a bunch of experimental groups and theoretical groups are basically putting together a large set of observables, and even at dimension 6, they're trying to draw inference from the data in terms of the global constraint picture, because that's what you need to do in this SMEFT. I emphasize you need to do that, and it's actually happening already. So what is being shown here? It's a very complicated plot, but what's being shown here is classes of experimental observables on the top. Top physics, Yukawa measurements, so Higgs measurements, diboson measurements, and electroprecision data like LEP1. There's individual Wilson coefficients listed here, and then the color coding is how much of a particular eigenvector of constraint is coming from particular Wilson coefficients. How much is dominated by a particular Wilson coefficient is what's being shown. So what you find here, and this is a log plot, this is the eigenvector of constraint. So what people did is they combined up a lot of data. They basically diagonalized the Fisher matrix. They basically lifted all the flat directions. They diagonalized the Fisher matrix. They took the inverse. And they found the overall degrees of constraint, which correspond to combinations of Wilson coefficients. Those are eigenvectors of constraint. And they just decomposed the global constraint picture into this basis of eigenvectors of constraint. And the constraints that they get, this is TV, and this is a log plot, are extremely hierarchical. I mean, this is just, as you understand, it's a log plot. The fact that it changes as much visually tells you that they're very hierarchical constraints. Very weak constraints are being combined up with very strong constraints. And this is all stuff that doesn't violate symmetry. So you can't use the symmetry arguments I was telling you about to distinguish this sort of story. This is what's happening in the set of parameters that project in at dimension 6, which are all basically on the same symmetry footing. It's not symmetry that's causing this. But this is the story, and then what's the numbers over here is essentially how much of the constraint comes from different classes of observables. Okay, so this is the sort of thing that's already being done by multiple groups and by the experimental collaborations, at least internally now, and there are some results at ICHEP you can see, like this. And that's interesting, and we want to basically get this pattern, and we want to get it better over the next decade, 2 decades, and we want to use that pattern if we see deviations like the W mass deviation and other deviations to really follow some underlying new physics. But this is not a perfect description, right? This is something where you just do something at dimension 6, but you're neglecting the dimension 8 effects. You're neglecting a lot of loop effects, keeping others. So it's not perfect, of course. You want to know how wrong this is so we don't get misled in the pattern we're trying to follow when we actually find real deviations. So we basically need to know the theory beyond leading order to basically know how wrong we are when we interpret these sorts of deviations at leading order. So can we do better? Yes. And I'm going to motivate now and show you how we get to results like this. So there's 2 things about the previous slide which maybe would bother you if you thought about it carefully for a while. One is there's all these constraints being shown on eigenvectors of constraints. And then they're being decomposed to individual Wilson coefficients. But what I've said and what you should know is that individual Wilson coefficients are not themselves physical. You can do field redefinitions and remove some of those Wilson coefficients and change bases. So can you go in a direction which is less Wilson coefficient dependent and is more aligned with what's actually appearing in the observables? And secondarily, it's just a bit curious, essentially, that we get these eigenvectors of constraint. Maybe we should be thinking more generally of what those eigenvectors mean. Okay, so what I'm going to show you, what we're going to get to, is we're going to get to understanding expressions like this. So you can basically write down Higgs to gamma gamma as a 3-point function. You can brute force this at dimension 6. But what you can actually show, and I'm going to try and motivate this to you completely, is that this is the closed form answer in the v squared over lambda squared correction. This is the complete answer with an equal sign, including all corrections. And it's written for a perturbation to Higgs to gamma gamma from these effects, which can be physics beyond the Stern-Model effects projected into the SMEFT. And it's decomposed into kinematics times this whole thing, which is geometry, okay, field space geometry. And the field space geometry is what lets you write this thing down in closed form in such a simple way. And we've seen some of these metrics before. These variations of metrics appear. These couplings have bars on them, so they were canonically normalized couplings as far as you were concerned at dimension 6 when I talked about them before. But we're going to start to interpret them as geometric couplings. We're actually going to understand that the canonically normalized couplings that we brute force at dimension 6 are actually the geometric couplings that correspond to the standard model couplings, which is like a flat field space limit of this underlying geometric structure in the EFT. So that's rather remarkable that you can write down an all orders form answer like that. Whenever you can solve something in field theory in a complete closed form, kind of trivially, you should probably pay attention to what happened and figure out why something so nice happened for you. Because we really didn't expect this, but this just dropped into our laps when we started to do this sort of thinking. So what's underlying this is something I mentioned to you, but I just want to reemphasize this point because I think it'll make it clear. So why is this happening? I mean, why is this working at all? It's working because the basic principle underlying what is appearing in the experimental perturbations, how we actually wrote down an operator basis itself, if we worked on a closed form operator basis that was non-redundant, we used field redefinitions to basically remove some forms and fix our field variables to basically write down something to calculate with. And because we used those field redefinitions, that's a principle essentially that's underlying how we're writing things down at dimension 6 and dimension 8. So do the field redefinitions themselves and the field redefinition variance, which is how you're using them to write down the formalism, do they have another effect? And they do. The effect they have is that the only things that will then appear in the amplitude perturbations are things that are field redefinition invariant. And that means that they have to be basically capturing properties of some abstract field spaces which basically characterize the geometry of those field spaces, right? Because those are the things, it's like when you have a coordinate system, your coordinate system, the curvature of a space doesn't depend on the coordinate system you choose to basically write down your coordinates in that space. It's a property of the space itself. The field redefinitions, you can choose to change your field variables, but the properties of the field space are the things that are field redefinition invariant, which is the things that are appearing in observables, because observables are field redefinition invariant. So it's just like in general relativity that this general coordinate invariance leads you to actually use tensors that represent that general coordinate invariance and basically how you write things down. Now we have field redefinition invariance, and that means we are going to write down things like these two-component object, these tensors you've seen over and over again, that are going to be what we use to derive other things. And then we're going to generalize this to higher endpoint functions, because that's the way it has to be in the field theory. Now again, I told you this before, but I'm going to remind you again, W curly here is 3 W's in a B field. This should be a W curly. And this phi is a real scalar field representation of the Higgs field. Yep? Right now, we're just basically going to do this as addressing a two-derivative operator. You can do generalizations of this where you start to worry about the momentum are also appearing in terms of field redefinitions. Yeah?
So they can be also depend on both the or not?
Not for these guys. Not these ones, not at the moment, yeah. But in general, like in a general sense, they can, but not in the formulation I'm going to show you at the moment. And the reason for that is we're going to, well, let me get to that. But yes, in general, yes. In practice, for this particular geometric construction, no. Okay, so this is stuff that again, I showed you these references before. Okay, let's focus in a little more on this, and I'm just kind of reminding you of what you saw earlier in the week, because hopefully the repetition is going to be helpful, and then we're going to dig into it a little more so you understand better why this is working the way it's working. Okay, so these two objects which we looked at, this tilde was the v squared over lambda squared times the Wilson coefficient. Now just at dimension 6, it has this decomposition of 1s, that's the standard model, that's a flat field space limit, the square root of this metric. And then these tildes, they appear, these off-diagonal ones. Remember, this one had to do with all of this weird stuff happening in the dimension 6 canonically normalized couplings we were writing down. And then these are the canonical normalization effects. And similarly for this guy, these are just two operators that appear at dimension 6, and they appear in this form. Now, first of all, you should notice that there's a lot of zeros here. And so even though I mentioned very briefly, and people have said in the other seminars at times, that these square roots of these metrics, these tetrads essentially decomposing the metric, that they are like veil lines in general relativity. They're not exactly the same because they are constrained by symmetry properties, right? So there's a bunch of zeros here that are going to be there at all orders in the expansion if they are going to be constrained by the symmetries that are associated with these indices. So even though it's similar technology using differential geometry, it's not exactly the same as general relativity. So remember that. Just keep that in mind. But nevertheless, these are very useful objects. Why are they very useful objects? Why is this thinking very useful? Well, as I said, and I'm going to say it again for repetition's sake, the point is what appears in the amplitude perturbations has to be field redefinition invariant. So it has to be geometric in some sense in the field space. So there's going to be decompositions where there's going to be functions of 4 vectors. There's going to be kinematics. And you saw in the Higgs width calculation, we were already starting at dimension 6 to organize kinematics times scaling effects. It's always going to be the case in amplitudes when you do this stuff efficiently that you go after kinematics times scaling effects. And those scaling effects are going to be geometric. That's the key point to realize, because they have to be, because you can isolate different kinematic forms by basically doing different experimental results. And so the individual guys have to be field redefinition variant. Yes?
So in your expression, you put the bracket for O1 but not on the N1 and 2. And so what's the meaning of this bracket?
That's just that I'm going to take some expectation values of some matrix element to get momentum factors.
So that depends on the initial final state?
Yes, that's right. So this is a labeled state. And so it has initial and final state. So it's just basically the expectation value, so it'll give momentum associated with the external states. That's why the bracket's there. Whereas this is like internal structure to the theory, which just has to do with the dimension 6 operator scaling effects, and dimension 8, dimension 10. Okay, so here's a way you can conceptually understand what's going on, which is a little bit different, but maybe it might be more kind of conceptually pleasing for you, or intuitive for you. Okay, so let's think about it this way for a second. In the case of the standard model, you know that what the Higgs mechanism does in the standard model when it takes on, it's going to be represented by green blobs here. What it does is essentially, because of the couplings and the interactions that you write down, it basically means that those states, as they go through the Higgs medium, they slow down. They bounce into the Higgs field, which is the getting of EV, and how much they hit the Higgs field is the coupling strength, so they get more massive. And the more massive they are, the harder it is to go through that medium, so that's essentially mass, right? They slow down. And not only that, the field theory organizes itself efficiently into degrees of freedom that have combinations of things that slow down in the same way, and that's the mass eigenstate structure of the theory. So that's fine. The Higgs field gives masses and mass eigenstates, right? Now, when you have these higher dimensional operators around, and you just have basically something like this, we're going to do Higgs to gamma gamma because it's my obsession. You can write down a dimension 6 operator, and if you take one of those Higgses to a VEV, then you have a perturbation, which can appear with the same kinematics for Higgs to gamma gamma. But you can also have 2 extra Higgs fields that can be there for a dimension 8 operator. In general, this can happen. And as long as they both get vacuum expectation values, same kinematics, same sort of structure in terms of perturbation, it's just an extra v squared over lambda squared contribution. And that's also the case for dimension 10 and 12 and so on and so forth. And you can do that while also there's indices here for these Higgs fields. They can be hit by symmetry generators. So when you're actually doing an experimental measurement and you're choosing your final states with brackets, and you're basically fixing those final states and initial states, you're basically also choosing how many Higgs fields you have in that experimental measurement. And a bunch of the Higgses are going to be assigned to VEVs. That's projecting into the physical structure. All of this stuff is there, even if we don't calculate it, and it's all collapsing down onto a perturbation, right? And then it has to appear in the perturbation in some form, in a way that's field redefinition invariant. It has to be, it doesn't care how you chose your coordinates for your scalar field, what actually appears in the amplitude perturbation. That collapse has to happen in a way that is going to be representing the properties of the Higgs medium that this interaction is actually occurring on. And that means it has to appear through geometries, what this gives. So just like in the case of the standard model, you get masses and mass eigenstate fields and useful interaction combinations which are appearing in the mass eigenstate Lagrangian, but it has to appear through geometries because basically there's no other choice in how it's going to appear if you realize that the field reduction variance has to represent itself that way. Okay, so that's exactly why this structure is here. This should be highly intuitive to you now that it has to be this way. It should go from what a weird way to write things to that's obviously the way you write things down. What else could you do? Okay, and now you've seen these guys appearing. I put them in the same color coding. I'm going to give you a little more definitional structure of these things now. Okay, so digging into these guys at dimension 6, you saw them before. It's a metric. And the only other thing I want to emphasize is there really are field space curvature tensors. You saw these in other lectures. You can take that metric. You can take variations of that metric. You can define Christoffel symbols, just like in the usual differential geometry. Because nothing about differential geometry was fundamentally having to do with space-time. It just had to do with basically geometric structure, essentially. And then you can also build Riemann curvature tensors. And the Riemann curvature tensors, very interestingly, will be non-zero exactly when you start to have these higher dimensional operators around. So it gives you another kind of perspective on renormalization and renormalizable theories like the standard model. Those are theories, essentially, which are flat field space limits. So the fact that you have this renormalizable structure in the standard model, which has this nice simple renormalization property, can also be interpreted in this way. It's another aspect of flatness in field theory. And it's when you actually introduce these higher dimensional operators that you get these curvature perturbations. Okay? Same with this guy. I've highlighted these in two different colors. Why? Because they're both dependent upon the background Higgs medium, but they have different Wilson coefficient dependencies. So they really are different spaces in a sense, because the different values of the Wilson coefficients, which basically indicate different UV completions, basically give different curvatures, because these Wilson coefficients appearing in these objects lead to curvature in the Riemann curvature tensor. So there's different curvatures associated with the different values of the Wilson coefficient. So there's more than one space. Higgs physics is not just one field space and curved field space. It's the intersection of many curved field spaces. And in general, the EFT should be thought of that way. It's measuring intersections of curved field spaces. Okay. So technical detail. We're using these real scalar fields. And if you want to look at the generators, they're just given here. So how do you get these generators? It actually is very useful to use real scalar fields. If you don't use them, let me just give you this little tip of how to basically derive generators like this. What you do is you basically take the usual representation of the Higgs field, and you have the Pauli matrix and the identity matrix act on it. And you look at how the individual components get changed, and then you map that change to the generators in the real field representation. It's pretty darn trivial, right? That's what you do. You identify these 4 generators associated with the usual representation that you're used to thinking about. This one has to do with essentially the hypercharged insertion. And also, if you square it, it's -1, so it's actually I, in a sense, in this real field representation. So these generators are around, and you see them appearing here in the covariant derivative acting on the real scalar field representation. And you also have this other guy, which is basically this usual generator times what I told you is basically I. And this combination of generators is also around. You need both of these things to represent basically all the interaction terms. Okay, if you look at the symmetry structure, though, of the symmetry, anti-symmetry of them, you notice a nice property. And they're useful because they have that nice symmetry property. So you can basically look at how you usually write down interaction terms, and you can decompose them in terms of these generators. And then just because the symmetry structure, some of these things are non-zero, where other things are manifestly zero. So by thinking of it this way, you can start to realize what you write down, you basically saturate all the possibilities that you can write down pretty quickly in terms of the index contractions. It just kind of makes it pretty manifest. When you have the Pauli matrix around, which is somewhat intrinsically linked to the SU2 representation, which can be intrinsically linked to the W's, in particular for some of the interaction structures I'm going to write down, it's a little bit limiting in your thinking. Because when you have that curly W, which is unifying the 3 W fields and the B field, you want to basically have geometric structures which basically couple the different Yang-Mills fields in this kind of generalized sense. So because the Pauli matrix lives essentially in a subset of that general structure you want to write down, it's useful to go to these real field representations for multiple reasons, but one of them is to just basically make it easier to write things like that down. And then basically the symmetry, the structure that it has makes manifest what you can write down and not write down. So this is an Euler result, okay? So this is actually the full answer with an equal sign of what this metric, this 2-component object can be, where I'm just looking at the scalar field dressings that can be there in the effective field theory expansion. We know the Hilbert series of the theory, so we know the operator constructions going by up mass dimension, like dimension 6, dimension 8, dimension 10, dimension 12. We know an explicit form of those, so we can actually check to see what we actually get there, and that there's only these structures as you go at all orders. If you just know to look at the theory that way, you can just pick that out of what was already known in the literature. So this is an infinite series, and it's essentially a v squared times a couple things you write down at low mass dimension. And this is just some particular generator structure using this real field representation, and that's also what's basically there, and then it has a v squared tower on top of it. So why is it that you can write down such simple things? The reason you can write down such simple things representing these geometric spaces is because essentially you're limited to these dressings, which are all basically representing the fact that these interactions and propagations are happening on a Higgs medium. And that means arbitrary Higgs emissions are being dressed up in terms of interaction terms. And it's arbitrary Higgs emissions and it's symmetry generators. But that's all that you're allowed to do. Now, if you have a field which has an index on it, which has to do with it living in a representation, and you're talking about the symmetry generator, then symmetry generator times symmetry generator with those index contractions basically have completeness relations associated with them because they're just symmetry generators. Those completeness relations reduce to delta functions once you have lots of symmetry generators around. And that's one of the basic reasons why it's not arbitrarily complicated. When you're talking about one scalar field dressing with possible symmetry generator insertions, that saturates in complexity at pretty low mass dimension. And at higher mass dimension, it just reduces to delta functions, i.e. h dagger h towers, or phi squareds, because of the completeness relations. And that's a generic fact which is present in all the stuff I'm going to show you, which is why it's not so complicated. So once you have these things in hand, you can actually ask yourself the following question, and you can do this mathematical exercise. Can I basically write down a generator that is associated with my weak eigenstates? Can I write down generator sets which are associated with mass eigenstates? And can I map between the two of them with those general geometric field space structures I wrote down, the Hij, the Gab, without even telling you what the individual entries of the matrix are? Like, if I just put them as general mathematical objects, can I do that general transformation and go from generator set to generator set? The answer to that is yes. And this, the consistency conditions in basically saying that you have well-defined mass eigenstates lets you to solve for this dependence on what these gauge couplings are, what the masses are, and what the mixing angles are. There's two mixing angles. One appears in the covariant derivative and the other is just in the rotation. But that's the set of objects that you need essentially to do this consistent mapping from weak to mass eigenstates, even without just pulling apart what the matrix is, what the metrics are. But it's just a math exercise of consistency, like map these generators to these generators. And that's really useful. Things like this in field theory, when you have like things like with powers like this stuff, they tend to be all orders results, and they are. And if we knew these objects at all orders, we'd be really cooking with gas, because we could just expand and do a lot of calculations all orders, and we would have the theory solved in one of the expansion parameters, one associated with the background Higgs medium, the v squared over lambda squared expansion parameter. And that's exactly what we have, because we can not only write down this guy at all orders, which you saw already, for the same reasons we can write down this one at all orders. Okay? And it's just a combination of math and physics going on that lets us basically do this sort of thing and have nice, closed, clean form answers of this form. Now, I told you before, when you saw these canonically normalized gauge couplings appearing at dimension 6, which is what's consistent with SMEFT sim, it was just a canonically normalized correction factor, which had to do with the Wilson coefficient appearing and what you thought of as the what you thought of as the gauge couplings. But here you can now to see and kind of understand these are the consistent geometric generalizations of the gauge couplings that are there in the standard model. Okay, that's what I mean by saying they're geometric couplings. They really are the consistent generalization of the standard model couplings onto these background field spaces. And we know both of these. I talked a lot about this. For the exact same reason, we can write down this. And it's the same reasoning. So you're addressing arbitrary scalar fields with generators. These completeness relations come in, and they make it so it's not arbitrarily complicated. And that's exactly why, even though it's a little more complicated here than here, and it has different Wilson coefficient dependencies, it's just phi squared towers on top of a couple things you write down. And the efficient way and simple way to write it down is to use these real scalar fields, so the symmetry structure helps you in figuring out what you can even write down at all. And it's really clean and quite simple to write down these structures once you realize to think this way. Okay. So when you have those, we talked a little bit about this in electric precision data, then you can actually do, and this basically getting those and some of those gauge couplings and such was basically this exercise of doing from weak eigenstates to mass eigenstates consistently. In this case of the standard model, the weak eigenstates and mass eigenstates, you know the usual story in your textbooks, right? It's just these rotation factors. It's just this rotation matrix. It just goes from this space to this space with a simple rotation. But if you actually think about what you can write down with contracting the indices correctly, and you think of these as like tetrads or Veil-binds, you really basically understand the thing you write down, which is straightforward, is the square roots of those metrics that you actually wrote down before. And that's basically all that can be there in terms of one scale transforming from weak to mass eigenstates. And it contracts the indices correctly, and that's basically what's going on. This generator I told you about, it appears here in this transform. And basically, it goes from how do you basically take the theory from weak to mass eigenstates at dimension 8 or dimension 10 to how else could you take the theory from weak to mass eigenstates at dimension 8 and 10. Right? Once you think of it the right way, the answer is unique and it's simple. And it just is the trivial thing you would write down just contracting the indices correctly, which is kind of nice. So now you understand why this thing looked complicated. Yes? Yep. 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 Well, it's just that this is, remember, you go basically to the W plus W minus. So those are associated with the W plus W minus. So there's always an I in there in terms of the field combinations that are there. Yeah. That's all that's there. There's also I's here, you'll notice. Yeah. Oh, wrong way. Now, when you saw this before, I tried to emphasize to you it was a bit weird, and it threw us for a little while doing our normalization work when we saw the stuff at dimension 6, right? This transformation, all this structure, with this correlated appearance of this Wilson coefficient. But what you just saw tells you why this looked weird, right? What's essentially happening, what was essentially happening, and it took us a while to figure out, was we basically were looking at things, it's like you're basically trying to think about a curve in the wrong coordinate system, and then you start to get complexity when you start to think this way. So if you have a curve, a simple curve, you could think of it in polar coordinates, or you could think of it in Cartesian coordinates. If you think of it in Cartesian coordinates, there'll be correlated projectors on the x and y axis describing the curve. The appearance of the Wilson coefficient in multiple places is essentially because this is curved field space physics being projected onto interaction terms and fields which are kind of intrinsically flat field space, because they're the standard model convention, which are the flat field space convention. So that's why you get this correlated transformation conceptually appearing. It's because you're doing something that's really fundamentally curved field space when you do higher dimensional operator perturbations, and you're projecting it on your conventional thinking, which is really a fundamentally flat field space. And it's much easier when you just basically think of it in terms of curved field space terms. So it should also be clear how to go and do this sort of thing for other interaction terms, not just those metrics. What are we doing? It's not mysterious, it's not magic. What we're doing is we're basically taking the SMEFT and we're reorganizing how we write it down. It's still the same theory, but by reorganizing it, we're profitably aligning it with what will appear more in experimental results because of the field redefinition invariance. We're just basically using that to our advantage. So what we do is we basically split it up into things that have to do with the derivative expansion, Lorentz index carrying objects, derivatives, different kinematics, things like this are grouped there, and then scalar dressings and symmetry generator insertions of those objects. And we basically decompose the theory this way, and thinking of it this way is very profitable, and it's very efficient. Okay, and it also separates out the two expansions. I've been emphasizing that there's two different expansions in this SMEFT, and remember they have to do with the derivatives, so they're being separated here, and then the VEV, right? So we're also not only is this like kind of useful intrinsically, because one of the scales is associated with geometry and not the other scale, it also is aligning the expansion parameters with basically the decomposition that you're doing, which is geometric, which is very nice. Okay, so you wouldn't make much progress if by doing this, for the things you had to calculate, you had to write down arbitrary numbers or 2,499 geometric objects at dimension 6 alone, right? It would be something you could do, but wouldn't necessarily help you. It would just be like a basis choice, you know? But it's actually much better than that, because when you start to think about what we actually measure experimentally, we measure experimentally the things that are getting precise. They're basically things which have to do with resonance structures that we can see above backgrounds, and things that we can calculate very precisely in the standard model with the standard model resonances being there. And those are things which essentially are built out of 2-point functions and 3-point functions, as Cliff was emphasizing. Once you have those on your hands, you have a lot of calculational power in your field theory. So if you just ask yourself, well, how many of these objects appear for 2- and 3-point functions, when you're thinking about CP even phenomenology, it's just this 11 objects. That's it. We wrote down 2 of them. We talked about 2 of them a lot. One of them is just the potential, so that's pretty easy to think about. That's just pure scalar field. There's this object, which I'll define for you in a moment. And then there's this WWW interaction with indices and scalar dressings. And then there's a dipole operator, an anomalous thing, which I'll write down for you at all orders in a moment. That has to do with anomalous W and Z's. And then there's this Yukawa coupling. And then there's just the same for the gluon fields. And that's it. So if you could write down all of those at all orders, you would be cooking with gas and be able to construct a lot of stuff. And we've been able to write down these at all orders over 2 years ago. So we are cooking with gas. That's why we're doing all the papers that you saw at the start. Okay, now there's a convention choice here of removing derivative operators, essentially in how we're writing down what we're doing for 2 and 3 point functions. So be aware of that, but it's just like the standard convention choice that you remove derivative interactions with equations of motion at the start if you can in your field theory construction. You can always do a geometric approach, even if you didn't do that, but this is just something that aligns with the Warsaw basis and the Hilbert series outputs, so it's just a sensible thing to do. So when you do this, this is the sort of profitable thing that starts to happen for you. You basically, we talked about these two. At dimension 6, people could brute force things in terms of the number of parameters that appear. This is the number of different parameters that appear in the dimension 6 operator basis for all the things we talked about. Dimension 8, it wasn't clear what to do, but now basically with this organizational structure, we wrote down these things at all orders, so we know how many parameters appear at dimension 8. It's consistent with the Hilbert series we checked. And then the really nice thing is basically the complexity saturates at dimension 8 if you look at what happens in the number of parameters. And at dimension 10, there's really not much more. There's one extra thing that happens for this guy. But it's basically telling you also if you write the theory down, if you can calculate the theory out to dimension 8, you're not going to get a lot of different weird anomalous kinematic populations which will screw up your interpretation of experimental results. And that's really a powerful thing. The color coding here is what these things are physically. Masses, couplings, triple gauge couplings, Yukawas, and so on and so forth. And you're going to see those on the next slide in terms of how the number of parameters appear compared to the general Hilbert series. Oh, not the next one, a couple ones. So let me just show you this one. This is another example, just so you can see you can write them all down. So this is a derivative phi field strength, dressing of that. These operator forms come in. This is one is kind of interesting because you have to go to dimension 10 for you to get the final operator form. It's given here. It's not to do with anything other than just more SU2 index contractions. And here it is written down in closed form. Again, it has the same sort of structure, a couple of structures up to dimension 8, one at dimension 10 in this case. You write down a real field, so it tells you kind of what to write down. And basically, then you're done at the end of the day. And you can write it down in closed form. Now, this is what I was going to get to. This is basically the number of parameters, how it grows as a function of mass dimension, dimension 6. This is not 2,499, but 3,045 because you added the baryon number violating operators in, but it's mostly 2,499. One generation, it's this 84 parameters. That's what's there at dimension 6. This is in the Hilbert series. What's there at dimension 8 is given here. And it goes up to 45,000 roughly in terms of number of parameters, number of operators. Dimension 10 goes to 2 million operators, 75 million, billions, and that sort of thing. And this is pretty bad. So with this complexity in the theory, you might think it's hopeless. We can't calculate because the number of parameters is going on. All the parameters that will come into our interpretation of experimental results out of control. Just stop doing this stuff. It's stupid. Just do models. But actually what's the case is the stuff that's experimentally going to be precisely measured and interpreted in EFTs, they have this property, which I emphasized to you came from the underlying symmetry structure of this theory, that when you're doing things that are basically precisely measured having to do with the Vev expansion, you can understand them geometrically, and they actually saturate in complexity. They don't go up in the number of parameters as a function of mass dimension of the operators. Right? So they're just rescaling effects of things that you can interpret at dimension 6 and dimension 8. So you're going in this direction, you're getting a lot more calculational power. And that's exactly what the geometric SMEFT is. People asked me about this week. This is exactly what the geometric SMEFT is doing for you. It's exploiting this. These are like tails of distributions. We had a conversation about this sort of thing. And the number of parameters going up so much. Well, what's actually going in the case in terms of what is going to be measured precisely when you're having standard model resonances in the game dominating phase space is much simpler. And we can do much better. So we're going to be in cooking with gas pretty quickly with interpreting experimental results. So let me give you an example of how to use this stuff in detail. A couple of examples, actually. I showed you electric precision data at dimension 6. It was not able to be calculated beyond dimension 6 for decades. And once we understood this technology and it was done, we calculated it in about 3 weeks. Okay, so it tells you how powerful and simple this sort of approach is in terms of doing some calculations you couldn't do otherwise. So how did we do this sort of thing? So we want to do electric precision data out to dimension 8. So we want to have basically these arbitrary Higgs dressings because electric precision data has to do with this resonance structure in the standard model, the Z pole. and you have arbitrary Higgs emissions. So you have to have basically the WZ coupling to fermion bilinears understood at all orders in v squared over lambda squared. And you basically also need to worry about anomalous connections that can come in of this form in field space that basically can lead to electric precision data perturbations. This is going to be highlighted in pink. You saw this one. This was just the geometric interpretation of the transformation from the weak to the mass eigenstate basis. This pink one is here. Same sort of reasoning as before. It's this structure. These are the operator forms. And you can write down in all orders. And it's the same reason you can write down in all orders. There it is in closed form. Okay? It's pretty straightforward for the same reasons. You can look at it later on the slides in detail. I just wanted to have the complete answer for you to see. Now, I told you before that this is this challenge of having to do these input parameter redefinitions at all orders as well, because we have to do that if we want to go to dimension 8 and dimension 10, not just write down these field space connections. But you can actually, by using the geometry, figure out how you actually infer some numerical values of Lagrangian parameters from observables. And you can actually write down things like this, which is basically how to numerically define these objects as well in terms of geometry, in terms of how you're measuring them. Okay? So the geometry also helps you write down these formulas at all orders. And then you can just expand the combination of them into an experimental result. The input parameters are also understood at all orders geometrically. Okay, so this is the combination that appears in the anomalous coupling of the Z to fermion pairs. This guy, the covariant derivative change, and then the expectation value of the connection. So if you expand it out, you can start to see something more familiar. Leading dimension 6 sort of corrections can come in here. Or dimension 8, dimension 10. But the point is the structure of the theory for Z, A, and W is just given here. This is like aligns with your usual thinking. There's bars here because they're canonically normalized couplings or geometric couplings. You now know how to think them. And you can see how the expectation values come in very simply. Okay? So then if you know that, if you can calculate widths, it's all the same. It just goes through the same sort of way. You're not changing the kinematics. It's just rescaling effects. And you can do electric precision data. So it's like this. If you basically think about this coupling, the expectation value here, the leading term is the standard model expectation value, which defines the Z coupling to fermion pairs. The P and R are flavor indices on the fermion pairs. The dimension 6 results you saw before were just the leading term in this expansion. And now we can calculate these dimension 8 results, which correspond to V squared, V to the fourth over lambda to the fourth corrections, just directly. We have the closed form formulas. We just put it in Mathematica and hit Taylor expand, and it does it for us. So the dimension 6 interpretation of these results, these guys are just given here for specific fermion final states and their chirality with their particular flavor indices. You can just see the numerical value that corresponds to the Wilson coefficient dependence. Just for completeness, I'm showing you. There's two sets of numbers because the two input parameter schemes are here, consistent with my policy of always doing things in two input parameter schemes. That's just dimension 6. Many, many groups knew that. We brute forced that almost 10 years ago. But the thing that people couldn't do was this, was figure out consistently how to go to dimension 8. And here's the answer. This is the same sort of structure. These are these expectation values at dimension 8. It's just numbers times Wilson coefficient dependencies or combinations of Wilson coefficient dependencies. So this stuff all comes from double insertions or quadratics, and most of it's not quadratics. We talked a lot about quadratics. They're not a good approximation really at all. And then there's a couple of new things at dimension 8. So when you first saw the Hilbert series going crazy, you might have thought, wow, at dimension 8, everything's going to go crazy. But this sort of thinking lets you understand at dimension 8, interpreting things like electric precision data or Higgs data, when it's not going to tails of distributions, it doesn't go crazy in the number of new parameters that come in. It's actually a very small subset of parameters. And most of the effects are just being consistent about getting cross terms at dimension 6, which is kind of an important thing to keep in mind. But we have all these numbers, so we have electric precision data to dimension 8. So how does it change things? Well, it depends how you ask the question exactly. So what is electric precision data? It's a lot of measurements of the properties of the Z. You can say, well, what about a deviation in Z to 2 leptons? Right? So in Z to 2 leptons, you can choose some possible combination of dimension 6 coefficients to give a deviation. And you can say, okay, now I can calculate at dimension 8 compared to dimension 6. And I can say the same numerical size of that deviation, how much would it change in its mapping from the experimental deviation to dimension 6 alone, or the experimental deviation to dimension 6 squared alone, or the full dimension 8 answer. And that's what's being shown here. It's an experimental deviation. The two lines are dimension 6 squared. And the shaded region is what you can have for the full dimension 8 result. So you look at something like this, and you say, oh, it doesn't matter. It's fine, right? The dimension 8 effects are small. They only get big when lambda is not too big. and nothing is really going to go crazy interpreting electric position data. So sometimes that's true, which is good. It's good to actually have that sort of calculational power to check these sorts of things. But it's more complicated than that. Because electric position data is not just the partial width decay of the Z to leptons, it's combinations of measurements. It's like forward-backward asymmetries. And a lot of the constraining power of electric position data actually comes from the fact that you're looking at observables where you have numerical suppressions in the standard model. In particular, the leptonic coupling of the Z, the vectorial coupling, is highly suppressed because of the Weinberg angle value. And for that reason, the forward-backward asymmetry is something that essentially is very numerically small in the standard model. So it leads to big perturbation changes when you actually write down dimension 6. So it leads to big constraints at dimension 6. But there's no free lunch. If you're getting these big constraints because of the numerical suppression at the standard model, then the dimension 8 sensitivity goes up too. And that's what's being shown here, just varying around some dimension 8 coefficient effects, how the forward-backward asymmetry interpretation gets shifted, and it's actually a pretty significant effect. And it's also something that happens in the alpha scheme. It's very scheme dependent. This is the W scheme, this is the alpha scheme, how much these effects show up. It's another reason to always do 2 input parameter schemes. And this is basically the forward-backward symmetry of the B, less of an effect, but still something to worry about if you want to interpret that, which has a bit of an anomaly compared to the standard model expectation. What's being shown here is 1 and 2 TV, what we would infer just picking 2 parameters just correspond to S and T, doing like the naive square thing, and then actually having the full dependence that you can now calculate of those parameters and how things shift in terms of how you interpret experimental constraints in the 2-dimensional plane. This is what I'm only showing you here is that it is very dependent on the cutoff scale. As you go from like 1 to 2 TV, things start to settle down, as you should expect. So it's not that electric precision data is like completely uninterpretable. It just means that when you do this naive dimension 6 projection, you should worry about these effects if you're in the few TV region interpreting your experimental results when you combine electric precision data constraints in the global fit program with Higgs data constraints. But now we have the technology to do that. We can actually ascribe errors of this form and just basically not overinterpret the data. The thing that I think is maybe most important, which is also being completely ignored, is that this, by the community in general, is that this obviously has very significant implications if we're going to go to like a gigaz's and we're going to like do super electric precision data measurements in the future. If that's going to be the name of the game for a while, then we obviously need to take into account these effects and be worried about this sort of thing in terms of interpreting things going forward. So I showed you that I'm obsessed with Higgs to gamma gamma many, many times, and I showed you this result. This result is similar in its construction to the result you just saw for electric precision data, but here it is in terms of these variations of field space metrics. And we did this actually first. And the reason we did this first is we were checking this sort of thing of, well, if you just square the dimension 6 amplitude, how much does things change compared to doing the full dimension 8 result? That was the purpose of this calculation. We were just showing people that squaring things doesn't work so well. This is the answer that we first calculated. And then this is the same thing that I was showing you for Z to 2 lepton in terms of a deviation interpreted at dimension 6 squared, and the full dimension 8 answer. And how that can change when you're sampling over the dimension 8 Wilson coefficients. This is like a 1 sigma, 2 sigma, 3 sigma variation, just doing a generic sampling of the Wilson coefficients that can be there at dimension 8. So what's happened here? Higgs to gamma gamma is showing an incredible sensitivity to higher order effects, whereas the Z to 2 leptons was not showing that significant sensitivity, at least that partial width measurement. So it's very simple to understand. It's just like the forward-backward asymmetry. If you have something numerically suppressed in the standard model and you do EFT perturbations, it's sensitive to higher order effects. And Higgs to gamma gamma in the standard model is numerically suppressed. It's a loop effect in the standard model. So that makes it sensitive to dimension 8 effects. And that's basically what's going on. That's what you're seeing here. Now, good or bad, it's the case that Higgs to gamma gamma and glue Higgs production are both numerically sensitive to higher order effects, and they're kind of key sources of information about the Higgs at LHC. So we have to take into account these sorts of errors. We need to think about how to think about these effects affecting our dimension 6 perturbations when we're interpreting them at LHC. Okay, you can not just do simple 3 points like Higgs to gamma gamma, Z to 2 lepton, or glue Higgs. Just to make clear, it's everything you can construct from those simple endpoints. Okay, so here's an example. A large part of Higgs to 4 leptons goes through Higgs to ZZ, and then you need the Z decay to 2 fermions. Well, you saw that we have that at all orders. So here's the Higgs to ZZ off-shell coupling, and it's just written geometrically here. There's 3 kinematic factors. It's always kinematics times geometry, and the geometric factors are different each case. And the same for the W's. but it's trying to show you that it's all geometric how you can decompose the Feynman diagrams. This is standard model light kinematics. It's always kinematics times geometry. And these two things are anomalous kinematics. So another thing that's useful about this anomalous kinematics is present at dimension 6, so it's in SMEFT sim. So when they do the sort of interpretation of experimental results, they don't have to worry about these anomalous kinematic factors. We have them. We basically have the simulation. What also is happening in this sort of approach is it guides you to understand when you need to start to worry about anomalous kinematics. When does something new happen at dimension 8 compared to dimension 6 in terms of acceptance cuts and that sort of thing? And that is first showing up here, and you know exactly how it shows up, and we know this structure at all orders. I showed it to you on previous slides. So we know exactly what's going on, and we can organize our thinking and check for these effects so we don't overinterpret the data as well. Good. So we can construct things that are higher endpoints out of lower endpoints. And it's still geometric. So this should hopefully be clear. I'm getting near the end. Don't worry. I won't go over. This is a general approach that we have now executed for a couple of processes that you can execute too, and you can do these calculations too. So let me just tell you the algorithm verbally, because it's pretty clear what to do, hopefully now. You want to take a result which is known at dimension 6, and you want to know what the result is at dimension 8. And we know the full complete simulation at dimension 6 because we have SMEFT sim in our hands. How do you go to dimension 8? Well, GeoSMEFT is efficiently organizing this, so you can go get the calculation at dimension 8, or you can just use this for errors at dimension 6 interpretations. You can still develop the formula this way. It's very, very simple. What do you do? So first of all, you basically can rescale the appearance of the tree-level Wilson coefficients with the anomalous dimension matrix, and that's going to be transparent to the simulation chain. So what that means is the logs for the perturbative corrections will be something you can infer from the standard model result, or from the dimension 6 result and the simulation dimension 6 result. So if you want to treat this as an error for the dimension 6 effects, if you don't know the full perturbative correction, you can infer the logs directly, goes through the simulation chain, and you basically can write them down by hand. Just take this stuff you wrote down in tree level at dimension 6, and you can figure out the log with the anomalous dimension. You can also figure out with this approach and this technology what part of the dimension 6 results that appears in the Monte Carlo output can simply be rescaled, and how it can be rescaled to generate the dimension 8 results, which don't have different kinematics, because we know exactly how to understand the v squared over lambda squared corrections and how they appear for individual Wilson coefficient dependencies. And sometimes it'll be the case that there's going to be anomalous dimension 8 bits, which you won't be able to just get by geometric rescaling of dimension 6 and just reusing the simulation results at dimension 6. But these bits are now identified. We know where they're coming from in the GeoSMEFT formalism. You can write them down directly and just calculate an individual process and put in the individual dimension 8 bits you need to put in. So this algorithm is sufficiently what we're doing over and over again to develop things to dimension 8 and also doing the full perturbative corrections along the way when we can. We've done it for these 3 processes, and the processes that this sort of thing is being done for will just continue to grow. And it's very straightforward. It's really, there's no magic here. This is exactly how we get this thing done efficiently, going to higher orders. I told you about the gauge fixing. I don't want to go over, so I was just going to remind you of this. It's not just that the structure, so the one thing you could doubt is like, oh, that all sounded great. But if it's the case that the perturbative corrections don't actually organize themselves geometrically profitably as well, then maybe it's just notation and it's just kind of some clever notational games you're playing. It's not really deeply anything about the field theory. The reason I was telling you about the perturbative calculations and how weird structure in the perturbative calculations showed up, which is also solved geometrically, is that sort of counter-argument is just wrong. It's not just the non-perturbative expansion, the operator expansion, it's also the perturbative corrections that you can understand better with this geometric approach. And that was having to do with the gauge fixing problem, which solved some anomalous weird results in Higgs to gamma gamma, and gave us nice ward identities, which basically we can understand geometrically, right? So the thing that I emphasized before, that there was the Z mass that appeared very nicely in the ward identities, it's exactly the all order Z mass that appears. So the ward identities you get geometrically, these are identities which are not just true for the perturbative expansion at all orders, they're also true for the non-perturbative expansion of all orders. It's an extremely powerful check of the structure of the theory, and it's fundamentally geometric. Okay, so this theory is geometric. Most field theories are geometric. Okay, this is my last thing I wanted to emphasize and then tell you what people can do if they want to keep working on this. I showed you Higgs to gamma gamma. This is the corresponding result for glue Higgs, this 3-point function. This is the dimension 6 piece that everyone can get that's in SMEFT sim. This is the cross terms, which are important. This is the dimension 6 squared bit. This is a dimension 8 bit that goes along with that, and these are the loop effects, essentially, with dimension 6 operators that you can get. You can do the same sort of analysis of a deviation and how much it changes in terms of your interpretation of fixed deviation for dimension 6 squared, and then the full variation over dimension 8 effects. It's a big effect. Okay? It's bigger than the current experimental errors. So if we have a theoretical error, which is bigger than the current experimental errors, we need to deal with that, because otherwise, if they keep improving the experimental measurements, we're still limited by theory systematics. Okay? This is a serious problem. It's true for Higgs to gamma gamma. It's true for glue Higgs. So what is the solution to this problem? I think the solution to this problem is essentially that you have to start projecting the experimental results into combinations of things which you can interpret geometrically, which are, not just dimension 6 results, but dimension 6 combined with dimension 8 rescaling results. And that's the sort of thing that we can actually do for a particular experimental result and interpret it. And then we can say, what is the residual error that's associated with doing that experimental projection, and then varying around the other higher order unknown things when we do that experimental projection. When we absorb, in other words, a bunch of these things and this thing into one combined object that we present the experimental results in terms of. What you need to do, what you need to worry about if you do such a thing, going away from individual dimension 6 operators to more geometric interpretations of the data in these global fits going forward, geometric combinations, is you need to worry about the fact that you have dimension 6 combined with dimension 8, and you're going to have subsets of higher dimensional operators absorbed into some of the things that you're projecting your experimental results on. That's usually bad in EFTs, because then you can do field redefinitions and you have ambiguities in how you're interpreting the experimental results at or you're inconsistent in the power counting. But here, because we can actually calculate the full answer, we can actually look at the residual uncertainties that's associated with the field redefinition ambiguity that's around, and we can compare if we introduce ambiguities which are bigger than the current experimental errors or smaller. So we have initially a situation where the theoretical error is bigger than the experimental errors. We do this reinterpretation in terms of geometric interpreting the data going forward. There's still an error and there's a problem we introduce, which is because of the inconsistency of the higher order effects. But then that error is smaller than the current experimental errors. So then we're in better shape doing it that way, even though it's not intrinsically all orders at the same time. Hopefully that was clear. That's what I think people need to do going forward in terms of interpreting experimental results. Like 10 years from now, we're going to be there. Okay, let me just tell you a couple things that we haven't solved yet to finish, because I'm basically done. So you saw this, but a lot of the stuff that you saw was actually tree level with v squared over lambda squared expansions. And I showed you can build up higher endpoints. But it's also true when you start thinking about loop corrections that you have to worry about 4 points going down into 3 points, right? So we need to basically execute those perturbative calculations, which I told you can be thought of geometrically. We actually need to figure out how to do that efficiently in code, and that is something that is an outstanding problem. There's intrinsic 4-point effects, higher endpoint effects, which are around. So you need to add those directly into experimental results. I told you the algorithm of how to efficiently organize your thinking to add in just the bits you need, but there's a lot of that stuff around to track down and define consistently, process by process. There's basically the challenge, if you want to understand more deeply what the problem is of extending the geometric approach to 4 points and above. The issue is that we are using the equation to motion, and we are basically doing something tricky here, which is basically based on amplitude technology, of how we're basically taking derivatives acting on fields, reducing them out to equation motion reducible structures and higher endpoints. Okay, so we were doing that iteratively in all the structures we were writing down and formulating the geometric SMEFT. And the real issue with 4 points and above is not that it's intrinsically non-geometric. By now you should hopefully believe it's intrinsically geometric because of field redefinition invariance. Is that we had a step, a math step, this one, that doesn't work when we basically go to 4 points and above. So if you can figure out an efficient way of doing those sorts of reductions in terms of your representations, in terms of the fields and derivatives that are around, which doesn't use that math step, you can also probably figure out an efficient way to go to higher endpoints, 4 points and above, in this geometric approach. That's an outstanding problem as well that people haven't solved. Okay, I think I'm done. That's it. So I'm hopefully on time. So this is an interesting sentence, right? So when I started doing Higgs physics really about 10 years ago, very intensely around the time of the Higgs discovery, I would never have thought this sentence is true. It just sounds crazy, right? What the hell are you talking about? But it's actually true. Higgs physics is intrinsically, essentially, the physics of curved field spaces. And by knowing that and understanding that, we can actually calculate and solve outstanding problems that are actually relevant for current experimental results and interpreting them. It's a rather remarkable thing. I never would have thought we would have gotten here. But that's the great thing about physics is like if you follow the right principles, it leads you in interesting directions, but this is really the right way to think. So hopefully it's clear that this is the right way to think. And I'm going to stop there.
Okay, thank you very much. Very interesting talk. Any questions?
All clear. It's good.
So actually, so in the beginning, you also introduced the curvature in the field space, and but in your result, you don't show anything involving this curvature. And what is the role of these curvatures and do they appear in the physical?
Yeah, so they appear, and they appear in amplitudes at 4 points and above, and if you did notice, I hope you noticed, that what was actually appearing here wasn't the curvature tensors, but was like variations of metrics and that sort of thing. So if you remember your differential geometry, you probably remember that metrics themselves are not necessarily coordinate invariant, but it's the quantities you derive from them which are, right? So same thing happens here. That's actually another reason why there's combinations of these metric objects appearing, not just one. It's that this combination is the structure that appears, which is actually the thing that is capturing a curvature property. So when you go to 4 points and above, the curvature is very efficiently captured by the Riemann curvature tensor. You have 4 indices, and it appears exactly in the amplitude, just right there. But when you're doing lower sort of endpoint interactions, what appears is these combinations of metrics which correspond to curvature properties, but it's not got intrinsically 4 indices. That's why it's essentially appearing in this form. You could ask yourself the question, what if I went to Riemann normal coordinates in some sense? Could I do that and make this sort of, reformulate the theory in some way where what appears is more manifestly the curvature properties? That's an open problem. I think people could make some progress on that, but there's an interesting fact that this is not Riemannian geometry, simple Riemannian geometry that's around here. So it's not the case that you can always go to Riemann normal coordinates in what's actually being shown here. It's the case for the pure scalar sector, but for the gauge scalar connections, you can actually go to Riemann normal coordinates. So it's a different, more complex geometric space. And some of these metrics, so this is something which we think corresponds to something people known about in generalized GR, and it's something called generalized geometry. But people are still working on essentially doing the differential geometry to basically figure out the most efficient formulation. But that's the short, maybe not so short, but that's the answer as to why it's not just the Riemann curvature tensors that appear. But they do appear in some endpoint scatterings.
So some of the recent papers you listed in the beginning of your talk. Yeah. I see.
Some of them, the Riemann curvature tensors starting to appear.
Yeah.
That's right. The papers coming out of Caltech recently and others. Yeah.
I see.
Yeah.
Very interesting.
Yeah, it's super cool. I mean, it's really, it's the right way to think. It's just, it's what's amazing about this stuff is how thoroughly physics is telling us the right way to go. It really is telling us to go this way. So we should listen and start thinking this way, I think.
So any questions from the audience? Yes, please.
For example, the SMEFT diphoton decay, I can see only the amplitude and some geometric, yeah. So, and also the corrected couplings from the.
That's right.
So I'm not sure. So, for example, explicit dimension 8 operator like the Murphy et al.
They're in here. This is not just dimension 6. This is also dimension 8. And
sorry. For because our Warshava basis operator, in your method, you can also derive the something like the Warsaw basis operator or something, or directly calculate the amplitude? I couldn't.
So what happens is that what we have is we have an understanding which goes to all orders for certain field space connections. And so it basically picks out a subset of the full higher dimensional operator basis. I should go back because this is actually another subtlety someone should sort out nicely. So the general Hilbert series goes like this, and it has this complexity. And we have defined something for field space connections which has a much simpler structure, which is a subset of this structure. But when you actually choose the conventions that we chose for the field space connections we wrote down, for example, when we write this down, we make a choice, and we say, look, this is the operator form that I want, which I want to have v squared over lambda squared corrections to. And so that's a choice. And that choice, just like at dimension 6, means that other operator forms should be consistent with that choice. So you have a non-redundant basis. So this is basically a choice, a convention that goes out from dimension 6 to dimension 8, dimension 10, dimension 12. But then one should go back and one should basically uniform the dimension 8 operator basis that's written down with this choice and dimension 10 operator basis and that sort of thing for explicit representations if we want the explicit basis. That's not been done yet. That also needs to be done. But this is a subset of the full Hilbert series. It's a subset of dimension 8 effects. But it's the subset of dimension 8 effects that actually does appear in Higgs to gamma gamma. Hopefully that's clear. Other dimension 8 effects exist. But when we're talking about a 3-point function like Higgs to gamma gamma, that's the answer that at least at tree level is the full result. When you have other things like Higgs to 4 leptons or associated production for Higgs decay, you have other dimension 8 effects that you have to get in, and those other dimension 8 effects can at times correspond to things which aren't built into the field space connections. So there's a couple extra little bits from here you have to pick out from the operator basis and add explicitly by hand. But then it's much a smaller part of the full calculation. You can just do that by hand and add them in piece by piece. Is that at all clear? I'm not sure I addressed your question. Maybe you should ask your question again.
Oh, yeah.
Is it okay? Or?
Yeah, okay. Thank you very much.
Oh, thank you for the actually, I have a question about the gluon sector. Can we
Which
extend,
sector? Sorry?
Can you extend the metric tensor for the electroweak sector to include also the gluon?
Oh, yeah, you could if you wanted to. There's no real profit of doing that. We've played around with that,
right.
But you could do that if you so wished. Yeah, it just doesn't help you because it's like block diagonal, so it doesn't do much.
Is it because Higgs sector is independent of the gluon? I mean, Higgs is not coupled to.
Yeah, you can build that object. I know the one you're referring to, but there's a trade-off here of what's close to experiment, right? And if you build that combined object, you can build it as a pure mathematical object, but whenever it projects into an experimental result, gluons are very distinct from electromagnetic states like photons and Z. So you can build it in, you can do some stuff with it as a combined object, but then when we actually use it, it'll be projecting out in 2 directions. So it's not going to be a useful object in terms of calculational simplicity.
I see. Yeah, thank you.
Any other questions?
There's a question at the back.
Yeah.
I was wondering how you deal with the RGEs, i.e., do you define this this geometric operator basis, and then you have an RGE flow matrix, which is shifting in between those different operators?
Yep. That's true. It doesn't close under normalization. That's why I said the statement 1 scale. But news from the future. It's really great in lots of different ways. And you should think that if this is true, and the perturbative structure has the structure that does, and the award entities work the way they do, that the RG you should be able to understand geometrically as well. So that's being looked at. It's something I looked at, I started working on, but I've been just talking for a year. But some of my collaborators are still working on that. And it turns out with heat kernel techniques, you can calculate a lot of the RG geometrically. It's kind of remarkable. You can do the thing that Tuft did for heat kernel construction, the derivations of anomalous dimensions, and it just, the generalization works rather directly. And it's another way of calculating quite directly and simply the renormalization group evolution, recalculating the dimension 6 result, and also getting higher order results at the same time. So the theory is geometric in its RG evolution too, but that's news from the future. It's not published yet.
And so the basis is, or let's say if you generically take a basis, then in the RGEs, you have good choices and bad choices, i.e. in some bases you have rapid movement between.
What actually happens is you get generalizations of the Kalman-Semantic equations, which are actually geometric in character. So you start to talk about the running of the Riemann curvature tensors themselves.
I see.
Yeah.
Thank you.
Yeah. It's not out yet, but it'll appear. Yeah.
Okay. Any other questions or comment? Any questions from the Zoom audience? I don't see it. So let's thank the Professor Michael Trott again for very interesting talk. Thank you very much.